Thank you for being here. I am Xiaoning Sun from Nanjing University of Science and Technology to present our work, NeRMo, Learning Implicit Neural Representations for 3D Human Motion Prediction. For a quick preview in this work, we introduce the background and challenges in human motion prediction. To address the issue, we reformulate current human motion prediction task from the continuous perspective, which represents the human motion as a continuous function to approximate the temporal dynamics, parameterized by a neural network. We propose an efficient meta-optimization to learn strong inductive bias for extrapolation from data. Experimental results show that our method can achieve improved prediction performance based on complete and incomplete historical observations. Formally, human motion prediction task aims to accurately forecast the future motion conditioned on the historical observed movements, such as the following sitting and walking motions. Here we show two classical human motion prediction methods. We can find that both of them input past human poses, model the spatial temporal dependencies, and then output future human poses. Existing methods predict future human poses as a function of the historical observations, which can be represented by this formulation. We call them historical value model. In fact, they always focus on dedicated network structure to capture the spatial-temporal relations. However, such discrete modeling ignores the underlying continuous temporal dynamics, thus only inferring the motion at predefined discrete time steps. It also suffers from considerable performance degradation when handling incomplete observations. Actually, incomplete raw motion data is frequently encountered in real-world scenarios, even when using professional motion capture devices. Our key idea is to learn an implicit neural representation which represents motion as a continuous function to approximate the temporal dynamics. The figure illustrates the overview of the proposed method. The disentangled spatial temporal representations are fed into a codebook coordinate attention. The backbone consists of several MLPs and a mask-aware spatial attention. The meta-optimization framework is designed to learn strong inductive bias by a bi-level optimization. At inference, the proposed method can simultaneously handle missing values and predict future poses. First, our neural motion representation disentangle the spatial and temporal information as this formulation. To address the problem of spectral bias, we use Fourier features as our frequency embedding to map the temporal coordinates into a higher dimensional space. Moreover, we exploit the neural contained in codebook to enrich the feature representation of spatial temporal coordinates. Then we propose a meta-optimization framework. Our motivation lies in that vanilla INRs are required to encode each motion into a separate continuous function. Another critical observation is that vanilla INRs struggle with extrapolation across the forecast horizon. As shown in this figure, given a past motion, vanilla INRs can well fit the observed window, but achieve significant decline for the predicted window. Our meta-optimization framework is designed to learn the strong inductive bias by a bi-level optimization by categorizing the parameters of INRs into two types: personalized modulation as instance-specific parameter and generic rule as instance-agnostic parameters. Specifically, generic rule is responsible for learning inductive bias from diverse human motions, while personalized modulation aims to adapt rapidly to the historical motions at test time. During the inference process, our goal is to estimate the value for future timestamps based on the incoming observations, including conventional setting and incomplete past motion. We first fix the generic rule parameters and then compute the personalized modulations for new samples. We conduct experiments on human 3.6M CMU mocap and the 3DPW datasets. We use mean per joint position error on 3D human joint coordinates as our evaluation metric. For a conventional setting, we predict future motions based on complete historical observations. The results of baselines and our method on human 3.6M dataset are shown in this table. We also report the prediction performance on CMU, mocap, and the 3DPW datasets. We provide visualizations here. The motion named grating is from human 3.6M. When predicting future motion based on incomplete observations, the proposed method achieved the best performance. Finally, we conduct ablation study to verify the effectiveness of our spatial temporal representation, meta optimization, and model architecture design. Thanks for tuning in.